Hello, everyone. This is Theoretically Podcasting. I'm Vasu Sham, and today I'm joined by Matt von Hippel. Hello, Matt.
Hey, good to be here.
Yeah, so what we're going to talk about today are the ABCs of modern amplitudology. In other words, all the things quantum field theory does that statistical field theory does not. Is that a fair characterization in your view, Matt?
Sure, that seems oddly specific, but sure.
Well, I only say that because of all of the motivational talking points around it, where you go, you see, you have this set of rules about Feynman diagrams and Lagrangians, and it's all very cumbersome. And if only you realize that we live in this nice Lorentzian world where answers are constrained by certain features such as kinematics, Lorentz invariance, and so on, then life would be so much simpler. So let's see if that's gonna come across in our discussion today. So here's a little document that we can run through, mostly based on this reference that Matt recommended that I read, and presumably so should any interested I don't know, Amplitudes enthusiast who's just trying to dip their toes into the water. But it seems like the starting point for all of this, which is okay. So my title is ways in which quantum field theory is a little bit more than statistical field theory, as we just discussed. And it seems like the starting point is really to take seriously little groups and well, start by what they are and then understand sort of how to exploit them. So it's sort of saying little groups meets spinners meets complexification, and all of a sudden we can do something that would take a very long and painful exercise involving Feynman diagrams to do. That's sort of going to be our motivation. But before that, just remember that if we wanted to find irreducible representations of the Poincare group, which is what we imagine particle states to really be, then what we first start by doing is we pick a reference momentum, either time-like or null, for massive or massless particles, and then look at the subgroup of the Lorentz group that leaves said reference momentum invariant. So it's like, in general, we can just take a time-like vector, put it into the following form, say, and then ask, well, what's going to preserve this particular vector, which is sort of similar to saying, well, you really have this on-shell condition in general, in absence of picking some reference momentum. And then that defines a kind of hyperboloid. And then, well, what's the stabilizer subgroup of a point on a hyperboloid? Well, it's going to be the rotation group. And go down to 4 dimensions. The relevant rotation group is going to be SO3, and the labels associated to it will be the spins. So the representations of the double cover the rotation group. And similarly, play the same game with null vectors. And there what we find is that the subgroup of the Lorentz group that preserves given reference null momentum so this now defines a light cone. And in general, of course, what preserves a point on the light cone is something slightly non-compact if we account for the boost. But let's set that aside for the time being for reasons we can talk about a little bit. Then all we need to do is look at rotations around the xd axis that preserve this vector, which will give us this SOD minus 1 group, which when we go down to 4 dimensions again, play the same game, is going to be SO2 or U1. And these are the sort of 2 starting insights. So the second insight is going to be playing a bigger role than the first in whatever bit of this review article that I will cover. But before proceeding, I'd just like a little bit of your opinion, Matt, which is why do we not see the rest of the actual stabilizer subgroup of this thing? Why does nature abhor these continuous spin representations? If you've ever looked into it.
Hmm. I mean, there certainly are people who kind of play around with continuous spin representations. Each sort of phenomenologist, so I don't know whether they're actually looking for it in a phenomenological context. Um, Heck, I vaguely remember there being people at Perimeter Breed were doing this kind of thing, though maybe I'm mixing it up with someone else. Um, but yeah, I mean, part of it, it's kind of an interesting question whether there's something sick about these kind of things. And it's true that when one tries to put together a field theory with something continuous spin, it's definitely not as trivial to do as the usual representations we like to work with. That
Indeed.
may or may not be a real answer, but I mean, for some bizarre reason, nature seems to mostly give us things that we know how to do. Maybe that's our
Right.
bias showing.
Right. Yeah. Well, it would be fun if some of you guys decided that, well, all these sort of Lagrangian building efforts didn't seem to get very far, but maybe we can, for instance, recurse our way into pieces of amplitudes of these kinds of continuous spin particles and see if they're possibly consistent with other things. And I think that that's kind of the vein in which some of these people that you mentioned, probably like Natalia Toro, Philip Schuster, were like looking at it. They're saying, well, okay, can we define soft theorems, for instance? And they made a little bit of headway. But yeah, this is just one of those things that I like. I don't know, asking people about, because it's a relatively understudied, well, quite understudied topic. And if there is progress, chances are you wouldn't hear about it. Well, yeah, depending on where it came from,
Yeah.
but most likely. Um, yeah. So, but for now, our starting point is this realization that the irreducible representations of massless particles are labels associated with representations of SO2/U1 called oscillicity. And let's stay in 4 dimensions for the time being, and jump into this review. So there's sort of 2 parts to make this whole modern understanding of amplitudes work, as far as I can tell, which is to say, first, realize how cool little group representations are, how powerful they are, but then to really exploit them, sort of jump to thinking about spinors more, and sort of momentum vectors and their associated kinematic invariance less, or rather, like try and build things out of spinors, specifically solutions to like the massless version of Dirac's equation. So this seems to be like the real sort of most elementary building block of a lot of what is to follow. So if you recall, for our audience, we have these 2 solutions to Dirac equation for the free Dirac equation for positive and negative energies. And P slash means contraction of the momentum for vector P with the Dirac gamma matrices. And for the massless case, we have that M here goes to 0. And what we have is that U plus is identified with V minus, and vice versa, U minus is identified with V plus. What's more, there are states of 2 definite helicities that are the eigenstates under this projector, which is 1 plus minus gamma 5. And then we call positive helicity the eigenstates of 1 plus gamma 5, the negative ones 1 minus gamma 5. And so, roughly speaking, we can imagine this to be some 2-component object in the space of positive and negative helicities. And when we have masslessness, just one of these slots is occupied, so to speak. So we've gone down from essentially some problem involving these spinors, which start life having, say, 4 components, down to 2. Right. So that's kind of our first hint. So if we zoom in and give this a name beyond U plus or V minus, let's call it lambda sub alpha. And similarly for U minus or V plus, which we call lambda tilde alpha dot. Yeah, so the dots always come with the tildes. And then the upstairs top, like the upstairs always comes with the tilde, and the downstairs always comes without the dot.
It's a highly redundant notation.
Yeah, exactly. This is just to clarify that there's a little bit too much going on here, but but just to be very clear, these things tend not to decorrelate. Then the massless Dirac equation is just the following in terms of these new symbols, ket p and whatever this thing is. I don't know how widely used this notation is, but
I mean that's pretty widely used, but I mean we just call
okay.
them angle brackets and square brackets.
Right. Okay. That's sort of what we're building towards. But now we sort of have half of what we would normally look at in the context of say gauge theory amplitudes or whatever, and that's why we have just the one bracket appearing here, and it'll be clear as to why. Okay, so now what we then do is realize that you see the contraction of the form momentum with gamma, which is this sort of P slash is itself the following kind of matrix, which involves these two things, where we've traded seemingly the one vector index for the pair of these spinor indices, dotted, undotted. Once again, downstairs, undotted preceding dotted is kind of like the same kind of rule where, if you have upstairs, the dotted precedes the undotted, and so vice versa, but that all follows from the following convention of these sigma matrices. This is sort of like sigma matrices extended by identity, and we define p alpha dot alpha as the following matrix of linear combinations of the components. And the basic observation here, if I can sort of give myself an extra line, is that the Lorentz invariant thing, which is p squared, is basically given by the determinant of p alpha dot alpha. Let me just correct all my various issues here. And what is that going to be? It's going to be p0 squared minus p3 squared minus the whole of p1 squared plus p2 squared. So it's just going to be p0 squared minus all the rest of the components, which is what we know. I'm not going to write it out, but it's what we know this object to be, given a certain signature choice of the metric. And this coincidence between contracting vector indices and taking a determinant over pairs of spinor indices is it's really a manifestation of the relation between the Lorentz group and SL2C, which is sort of another one of the starting points of this entire set of insights that will follow. So what we are doing here is utilizing this connection to think in terms of these objects with the spinor indices rather than these vector objects. Now, what's cool is that when we have a massless particle, the determinant vanishes, so the rank of this matrix is 1. And we can write that as a product of the things we met before, the solutions to the massless Dirac equation. And these are now the objects, the helicity spinors, solutions to the Weyl equation, which sort of automatically encode on-shellness of the momentum. And that's another sort of key property, right? So it's like, it seems that to really get a lot of mileage out of being in Lorentz and signature and so on, it helps to go on shell. Like this seems to be like one of you guys' favorite things to do, which in some sense is it's one of those circles we go in where we start off by learning that quantum mechanics and specifically the path integral does these things where like you could never imagine that a classical particle does whatever this thing says it does. It's got all these off-shell paths, and then you're like, okay, what do you use this path integral for? Or to compute these amplitudes, you see. And then it turns out that in order to study these amplitudes, it's very useful to encode the on-shell properties, it's sort of like really exploit the on-shell properties a lot, which is to sort of ignore those various wacky things the path integral entertains particles doing.
Yeah,
So
I mean, one way of thinking about it is just you're trying to calculate an observable. So fundamentally, the thing you care about has to be expressed in terms of things you can observe. And the particles you can observe are on shell. Regardless of what the off shell things are doing behind the scenes or not, if you once you actually detect something, it's on shell. And so all of your vocabulary for describing these things has to in some way translate to something that talks about on shell objects. And so the
Right,
key is
right.
sort of express things as minimally as possible in exactly the kind of variables you need and no more.
Indeed, indeed, and so that's sort of the mature understanding of how best to think about quantum mechanics, and we can maybe come back to that point. Right now, we're still setting up um, the framework, so yeah, all this comes with the promise that we can do cool things, and Matt knows that. I recently learned that, and you all shall see. So what's cool is that when we complexify, so here's the fun thing. We're ignoring, or we're sort of setting aside for the time being whatever the off-shell backstory is, but we will entertain the complexification of momenta, which is not quite the same as saying that when we go on like off shell or something. It's not quite the same as a crazy thing that you'd never expect a free relativistic particle to do when you like really write down the path integral that technically you should be accounting for that kind of crazy trajectory too. But what we will do is just say we complexify Minkowski space and study properties of these amplitudes there. So somehow complexification is still a smaller crime than than the off-shellness. So that I think is cool. But when we complexify, what we find is that lambda and lambda tilde are independent variables, and we basically see that the little group acts by scaling lambda and lambda tilde in sort of opposite ways by some complex number. When we go back to real Minkowski space, there's this complex conjugate relation between lambda and lambda tilde. And what we then find is that this complex number is really just reduced to its phase. And therefore, we recover the fact that the little group is U1. So it wasn't that our previous analysis was mistaken. It's just that there's this complexification that allows us to set these two things free or independent of each other. So that's and this seems to be an old trick, right? So there seems to be like a lot of people deep in the past that were trying to get a lot of mileage out of complexifying momentum and looking at amplitudes from that perspective. And it just seems to me like there's this nice history where there was all these ambitions about using analyticity of these amplitudes once you complexify all the kinematic invariants, but then they complexified too much and it just became a really big mess to try to analyze these things. It's like there are too many things to take into account. And then what we're going to talk about today is sort of how you get to sort of like minimally complexify so as to still gain some insight without sort of having to deal with like multi-dimensional complex residue theorems and so on. Yeah, so it's unclear. So I don't know, like what would you say is like the general takeaway from this? How much is good to complexify? Like, or
I mean,
rather, I mean, yeah, sorry, go on.
this is a good point. I mean, the kind of old analytic S matrix philosophy is kind of undergoing a renewal now, and I think that a lot of this sort of pieces that people stuck with to begin with, spinor helicity, ideas like that we're discussing right now, worked because there were these very sort of nice self-contained procedures where you could complexify kind of the right thing, look at sort of purely some on-shell space that had a problem, and just add enough variability so that you can twist things around and do something interesting. But certainly, I think people are kind of curious now about whether there's ways to resurrect the old analytic S matrix streams using more recent mathematics, using sort of better ways to look into these things. So I wouldn't say that sort of complexifying too much was hopeless, but I do think that it was very, very useful for amplitudes to be able to look at things in terms of these massless objects because fundamentally you're dealing with quantities that are simpler. I think in guess matrix people were scared of massless amplitudes. Massless amplitudes have IR divergences. They're not well defined. You need to possibly do weird things with the asymptotic states, which maybe came up in your conversation with Nikhil, maybe not, I don't know. But the thing about massless things is that if you do just take them seriously, if you kind of run with, your massless particles, accept that there will be IR divergences at some point and kind of don't worry too much about them, then you find these very nice, crisp, well-behaved situations which tell you what to do. And then years later, you can start applying those lessons to other things.
Right. Right. No, that is interesting. Yeah, I mean, what would be nice is if through all this we sort of get some appreciation for why one would complexify any of these objects in the first place, given the motivation to try and express everything in minimal observable terms. And there might not be one answer to that. I appreciate that it might be that there's multiple reasons, and yeah.
Sure. I think one way to think about it is that fundamentally what you're trying to do is constrain functions. And we know from kind of, realistic and complex analysis that functions in the complex plane are much more powerfully constrained than functions on the real line. Just sort of from that alone, you kind of know that that move is almost always a useful.
Right. Okay. Well, that's a nice starting point, because that sort of threads through a few different discussions that have been hosted on this channel. But yeah, nice. So let's proceed and see how that plays out in this context. So here's a little bit more algebra to express the spinors in terms of the momentum components, which is just in keeping with that matrix that we saw from before, where we converted from P to P alpha alpha dot, and then we had those two when we took P slash and saw that there was the block diagonal structure, and then realized that P alpha alpha dot was the product of these two objects. It all comes together. So this is just an inversion of the relations we'd seen above. And on this space, this alpha alpha dot space, there are these Levi-Civita tensors with both undotted or both dotted indices. And that's the only thing we use to raise or lower these indices. And we can contract them using epsilon. So we can contract the lambdas and can contract the lambda tildes. And here we have the double angle brackets and the double square brackets, which are kind of like the other side of that single one we saw before. And we can, as you can expect, what we would normally think of as kinematic invariants are given in terms of products of these kinds of things. So we're going to start to see many objects written in terms of such symbols, and this is their origin. And to make that point, here's what pi.pj, or 2 times pi.pj looks like. So notice that when we're on shell and the particles are massless, that is the Mandelstam invariant Sij, and it's just given by the product of angle bracket ij times square bracket ji. And baked into all these conventions is, well, this other stuff that we discussed of having top left, bottom right, bottom left, top right, and so on for dotted versus undotted. And yeah, we'll leave that as homework to sort of sort out for whoever's interested. So great, we now have a language to sort of re-express what we would have computed, say, from doing some Feynman diagram calculation involving massless particles, which we would have written in terms of Mandelstam invariants, which are themselves products or squares of momentum variables, in terms of angle brackets and square brackets, which are all products of spinors. Cool. So now let's move up to amplitudes of massless spin 1 particles, or gauge fields. the thing to now deal with, in addition to momentum, are polarization vectors. And of course, there's color stuff, which we'll just set aside for the time being, but polarization vectors are these things now that come with, say, the wave function of some external state of a massless particle. Now, typically, they're constrained by a transversality condition and the following relations, which are all fairly standard. And what we want to do is then express these, which carry one vector index, in terms, again, of spinors. And so now, in addition to, so what we'll do is we'll bake in this transversality condition by having a little bit of what we had before, that is this lambda spinor. And then we'll have a reference spinor Xi, which is coming with a dotted index if lambda came with the undotted index corresponding to the negative helicity, and vice versa for the positive helicity. We're going to normalize by lambda Xi angle and lambda Xi square and lambda Xi angle, the other way around. And the arbitrary reference nature of these spinors is sort of understandable, just because we have some arbitrariness in whether or not in regular gauge theory amplitudes we can add something proportional to the momentum to these epsilons, and the word identities ensure that that's a sort of spurious redefinition, or just redundant description of the same quantity. And that's basically captured by being able to shift C. So if we shift C, we do exactly that. We shift epsilon by something proportional to the momentum, which by the word identities is going to, so the contribution of this extra part is just going to kill the amplitude. So we don't really care. Now, spin 2 is, as far as amplitudes are concerned, much like spin 1, except we have now this polarization tensor given by products of polarization vectors of the same helicity. And yeah, I mean, it's the same expression, we just have more of these lambdas and Cs. So here is sort of the building blocks of all the sorts of amplitudes that we might care about. And this is something that, now, before going into the analysis of tree-level amplitudes, here's a sort of in-principle question that I'm wondering if anybody in amplitudes thinks about a lot, which is, certainly, if we then bake in locality to the story, we will sort of get some understanding or some handle on sort of tree-level amplitudes. Now, the thing is that the quantum effective action, right, is this other thing which is sort of always tree-level, because you just integrate out all the quantum corrections, but it's not local, right? So presumably there's just some set of rules that there might be some mileage to gain from, to just say, okay, let's try to go after the quantum effective action, provided we can control for the kinds of non-localities we expect from doing this or that. And sure, I mean, it'll still be the quantum effective action on shell, presumably, which is a little bit less than the full quantum effective action. So there's this relation between gamma, which depends on background values of the field, which I call phi. And what we know is that when we go on shell, then this object has exactly all the information that the generating function of S matrix correlation functions, which we saw in, this is sort of for the people that follow the channel. So there's some relation like this, where this is the object that generates S matrix elements. So this is a thing that, if one does a lot of Legendre transforming and then sort of re-encoding LSZ, it can kind of prove. But at least this thing is, inclusive of quantum corrections. It's just not local. So I'm curious, is there any effort to try to capture this fellow?
Interesting. I mean, obviously for most of the sort of theories that people are interested in, it's hard to impossible to represent as non-perturbable. I mean, in the best behaved cases, there are examples where you can expand in something else. These sort of OP kind of setups. But so I think the relevant question there is kind of what is, if you're going to write down the full quantum effective action, like, all loop, and it's going to have some inherent non-localities in it, and you want to do this on shell to begin with, it's essentially equivalent. Okay, you want to write down the non-perturbative amplitude. And I think one of the major difficulties is this question of what is that made of? What are you allowed to do with it? Because certainly, unlike for, say, tree amplitudes, it's not just going to be rational functions. Unlike perturbative amplitudes, it's not going to be polylogarithms, which probably aren't going to be gotten to in the span of this particular version of the ABCs, but the classes of functions that up in loop amplitudes are at least pretty well understood, at least definitely at one loop and most of the time at two loops, with one example I keep trying to get people to pay attention to. But yeah, like, so I think there's some aspiration to sort of non-perturbative, but it's a lot of kind of playing around with special cases and seeing if you can get insight. In order to actually these kind of programs with it, you need to know a lot more about what a non-perturbative amplitude looks like.
Right. I see. Yeah. So I mean, it's just, you're saying that the family of functions is maybe a little bit too large to say anything too general once you start to sort of entertain generic non-localities and so forth. And then it's sort of hard to make sense of what's going on. Yeah, that's interesting.
The impression I get is there's sort of very limited cases in which one can make these kind of arguments, where there's some sort of non-perturbative argument that, well, they're kind of like FT bootstraps for amplitudes in various contexts. So, I mean, that's maybe the closest kin to what you're describing. And in that case, you're kind of breaking the thing down in, some set of objects that you can deal with. But still, there's only sort of certain things you can do with that at this point.
Nice. Okay, I see. Yeah. Okay, so it's a homework exercise, you're saying. But cool. Well, just one brief note about massive representations before proceeding to somewhat dynamical things. So here what happens is the first part of the story remains the same insofar as transcribing momentum vectors into these bispinors is concerned, except now the determinant isn't 0, it equals m squared. And then that means that there's full rank for this object has rank 2, and so you want to express this in terms of a pair of spinors, which now have this index I. So again, we have lambda, lambda tilde, and they have this index I that runs from 1 to 2, in addition to their spinor index alpha and alpha dot. And here, what we see is that the rotations between lambda I and lambda j, which is j is not I, are basically dictated by SU2 transformations. So we meet again the little group transformations as things that act on these spinors. So it's not impossible to talk about massive things in this context. It's just a little bit more detail to take into account. All right. So now let's have let's get some mileage out of all of this, of everything that we've done so far. And this is an interesting point. So the route this is going to follow, I guess, is the historical route of basically constraining and therefore sort of simplifying like gauge theory amplitudes, massless gauge theory amplitudes, and sort of tree level, even gravity amplitudes, if we're to get that far. But is there, like, I know there are efforts where there's just the effective field theory for some scalar fields, and specifically for if they're massless, presumably they're like some Goldstone modes or something. And so there's a nice treatment in terms of amplitudes of whatever those things do. But my sense is that people got to using these methods for those theories a little bit later, like after the sort of gauge theory use cases. So, I mean, like, why is that? Do you think?
Well, I think largely it's a question of applications. So
Mhm.
you kind of have to think about amplitudes as kind of two different threads in parallel. So you've got people who are sort of very interested in these kind of abstract, deep problems about, how do we talk about QFT? How do we represent QFT? But that group has kind of always been in dialogue with, it's asking a much more concrete question, which is, you've got some collider, it's pumping out data. How do we calculate background so that people can look for things? Right.
Right.
And that's, been true since I would say the field began with these calculations focused on Fermilab. And then later it's, really hit its stride with the LHC. But for those calculations, the biggest challenge has always been the vector bosons, the gluon amplitudes. You don't
Right.
get very complicated Higgs amplitudes, so you don't have to worry too much about massive scalars. And while you occasionally get massive fermions, that was often kind of the next step. These were sort of corrections to things that were maybe tougher to see. So the first kind of the beginning of the story, which I don't actually know if we'll get here or not because I don't know the order of things in this review, is something called the Park-Taylor amplitudes. And Park and Taylor, what they were trying to figure out is just tree level, 2 gluons goes to 4 gluons, the amplitude. And in 1986, when they were doing this, they didn't know.
Hmm.
People hadn't done that yet. This is, easy more than a decade after QCD had been written down. It's not like they didn't know the theory, but that was a calculation that was pretty damn painful for people to do at that point.
Right.
And a lot of how this field works is kind of taking those kind of challenges and having people think about them and see if there's a deeper way forward.
Right. Right. Yeah. I mean, it's certainly flashed in the introduction. We can sort of go back to that part of the notes, but I mean, it'll also feature as one of the things that we'll first meet, which are these maximal helicity violating amplitudes. So now, given that we've sort of set the stage, or like explain the motivation as to why gauge theory amplitudes were the first to be looked at in this whole context, and we can sort of see that despite the complexity of quantizing gauge fields, when we think about it from the Lagrangian perspective, that is the need for things like BRST, ghosts, and we need people like Zinjastan and like all of their friends, Simanzik, whoever, to prove things like the forest formula, and then proving the normalizability of this thing, you need to know first about the Higgs mechanism, whatever, and it's like fairly painful thing to do that almost no textbook talks about, just because they say, well, trust us, this works. Here's a toy model, and see you later. And maybe if you look into the details, you'd be glad that that's how it works, and that you're not subjected to all that in an ordinary course. But yeah, so for now, at least from looking at on-shell features, given the alphabet here, right, of what the polarization vectors and the momenta are in terms of these spinors, we just know that the amplitude has to be some function of these symbols we write down in terms of square and angle brackets. For now, let's just think of it in those terms, and then we can sort of refine what it's going to be. So then on top of that, knowing that the helicity, sort of the little group transformations act by scaling of the lambda spinors and lambda tilde spinors in opposite ways, means that the helicity is basically given by a sort of it's almost like a dilatation eigenvalue, except you're subtracting off the dilatation with respect to lambda tilde, and then you're adding in the dilatation with respect to lambda, because it's a sort of simultaneous transformation that it induces. And so from here, what's nice is that we can tell that A is probably a rational function of these spinors. And what's more, that the helicity sort of sets the difference between the number of powers of lambda and the number of powers of lambda tilde. Just from knowing this relation. So let's start with the 3-point amplitude, and with sort of spin 1. That's as far as the notes I've prepared will go. But it already highlights a lot of cool things. So the 3-point amplitude has the following feature when we go on shell in regular Minkowski space. It's 0. Why? Because P1 plus P2 plus P3 is 0. The only thing that you'd expect to appear in the amplitude is Pi.Pj. And now let's think about what happens. P1 equals minus P2 plus P3, and then P1.P1 is 0, which means that P1.P2 plus P3 is 0, which then you run this through every single one of these momenta. The same is true of all of them. You just run into the fact that Pi.Pj has to be 0 for any I and j, right? So this is like, should be a sort of fairly simple conclusion to say, let's move on. But also you could think, let's not, and see where we can go, right? So this is a nice thing about complexification, is that some of these conclusions can be averted. And the reason for that is when we complexify, lambda and lambda tilde are independent. So again, this story in terms of real momenta just automatically implies that both the angle and square brackets vanish for all particles, the products. But then this just assumes that lambda and lambda tilde have this complex conjugate relation between them. It's sort of baked into reasoning about angle brackets starting from the momenta themselves. However, if we take lambda and lambda tilde to be independent, then there's actually two solutions, right? Because Pi.Pj is a product of ij angle and ij square. So for that to vanish, we either have that the angle bracket vanishes or that the square bracket vanishes for all I and j. It's pretty cool. Furthermore, we see using 42 that the so if you look at the helicity assignment minus minus plus for sort of helicity s particles, then all we need to know is the sort of minus minus plus helicity amplitude with helicity equals 1, and then raise it to the power s. So that just comes from the scaling here, and the fact that this is probably a rational function as we described. So it's easy to see that that's very likely the case. And so let's just look at this. So let's take the case s equals 1, which is kind of a building block, and find that if we go minus minus plus, okay, well, the difference between the power of these and the power of these has to be, well, 1, but then we just noted that this vanishes, so it's got to only be a function of, or sorry, this vanishes, so it's only going to be a function of this, or vice versa. Cool. And so then what we need is just to have, so we sort of cover over one of the terms in this dilatation thing. So in this, we've got to have A coming out of taking this dilatation acting on A. So the simplest thing to do is just have the following, right? So we have 1, 2 cubed divided by 2, 3, 3, 1, right? So this satisfies the right scaling property. Or we do the same thing, but now we have the angle brackets. And for the same helicity assignment, that'll correspond to 2, 3, 3, 1 angle brackets divided by 1, 2 cubed, right? So again, it's because the lambda tilde comes with a minus, whereas the lambda comes with a plus, and that's why you have the 2, 3, 3, 1 appearing in the denominator in the first option, and in the numerator in the second option. And it seems that for gauge theories that we seem to have, the first one is chosen. So now that they do offer some explanation of this, but I thought I'd just ask you if you had a shortcut way of seeing this. Like, you know, is it just something that's empirically decided, or is there a sort of deeper reason, or sort of simpler reason to see it?
Sure. Well, I mean, the important thing to recognize is that the other object there is not necessarily useless. It just has different mass scaling.
Oh,
So
right.
Yes, so it's something that would have a different. So I mean, thinking about this as something that's, you know, got some coupling constant attributing amplitude, that would be, you know, not a dimensionless coupling constant. And so you can consider things like that if you're, say, working effective field theories, for example.
Right.
But for, the basic kind of nice renormalizable, um, in the case of gluon's renormalizable theory, the fact that you can take this to the S means you can also do it for graviton, for normalizable, obviously. Nonetheless, for sort of the leading terms in the effective action, you're looking for things with the correct mass scaling, and that means objects like the first one, not like the second one.
Cool, thanks. Okay, that makes sense. Indeed, it is still true that amplitudes come with the prefactors that are the coupling constants. So, okay, there we have it. We choose option one if we're looking at gauge theory amplitudes where we expect to have the Yang-Mills coupling appearing as a prefactor for it. And in some effective field theory, if there was some non-renormalizable interaction that provides us a mass scale for this object, it will probably also appear. Cool. So this is what we get. Now, same thing is true if we reverse the helicities, except now we're going to have the angle brackets, and that's called the MHV bar 3-point amplitude. And so I guess we should explain what M, H, and V here are, just the maximally helicity violating. So yeah, from what I can tell, it's like mostly one of the other kind type amplitudes, or one or two of the other kind type amplitudes. But I mean, is that the broadest definition?
So the definition is two of one kind in particular. Usually the way it is MHV is 2 minus helicity, all the rest plus.
Oh, I see. Okay.
Yeah, and then the bar is flipping that. Yeah, so the idea kind of is that if you've got, two initial things that are minus helicity, then you're maximally helicity violating if you're generating a shitload of positive helicity on the other side.
Okay.
Now you might ask, okay, well, you could go even further. You could have 1 minus and all the rest plus, or something like that. And this isn't visible for the 3 particle things, but for higher numbers of particles, the statement is at tree level that's 0. There's Ward identities that tell you that, in fact, you have 1 minus all the rest plus, you have all plus. I mean, you're kind of already seeing a little bit of this too. Okay, yeah. And these are actually kind of another that you're about to get to is sort of another example of an object that could have shown up and is needed in some effective field theory, but not something that's normally there. Yeah.
Right, I see. Cool. Well, yeah, so I guess the same logic applies to these objects when it comes to fixing their dependence on the spinors, because again, we have the scaling rules, and those scaling rules will just tell us that, well, we just need to have certain number of lambdas or lambda tildes appearing in A so as to satisfy the right solution to this equation. And what we're going to get will be pretty simple. If you have 1, 2, 3 all minuses, then you have angle brackets for 1, 2, 3. Similarly with plus, except you're going to have these square brackets. But if we just looked at what the coupling constant preceding this would be, then, well, in Yang-Mills theory, it would just be 0. And if you just included something like trace f cube or whatever, then you will probably have some contribution that looks like this. Cool. So that is really nice. And just to sort of mention, these are like prototypes of the kind of amplitude that Park and Taylor were initially sort of interested in, or like what they're sort of famous for computing. And maybe we can write it down at this point, because there's already, I think we have enough intuition here as to what it would look like if we just extended this to like I don't know, n, right? They had the like any n, where you have like stuff 1, 2, whatever, and then you had I minus. So these are all plus. Yes, that's just what you described here. That, well, we need to have all pluses, 2 minuses, plus I minus j minus all the way to n, which is also plus. Okay, so this is going to be something. I mean, I'm not sure. Will it still just be g? Whatever. It's something.
Well, yeah. Now it's g to a higher power, right?
Okay, so that we can give ourselves. Times it's going to be right. So here we have an angle, our angle to the power n divided by, well, the dot product of all the subsequent ones. Is that right? So we're going to have something like ij, and then we're going to have 1, 2. Okay, so this is my.
Let's see. So it shouldn't be to the n; it should be to the 4. The numerator.
Okay.
I just had to check that to make sure that I wasn't going crazy. But yes.
Okay. And the rest of it is right. You just have a string of these, or do you have some specific?
Yep.
Okay.
The rest of it's right. So it's in order. So it's 1, 2, 2, 3, etc. So these archetypal denominators. There's for some reason a lot of different contexts in which you kind of have some nice structure like that sort of shows some sort of cyclicity to it.
I see. Okay, that's cool. Yeah, so again, just to check, run this through here, and you will find hopefully the right scaling property for this amplitude too, and that's all very fun. But let's sort of work our way there, starting from this atom. And okay, so just in case you just think that we're pulling one over you, here's a Feynman diagram calculation starting from QCD. Just go through what it would look like. So here you just use the regular 3-point vertex, the Feynman room for 3-point vertex, and sort of write down what the tree level contribution to this amplitude should be, account for helicities in the polarization vectors, and notice that there are features such as this and the transversality of the polarization vectors that allow us to write this entire thing in terms of just these two combinations. So in terms of p2 dot epsilon 1 minus and p1 dot epsilon 2 minus, and with coefficients epsilon 2 epsilon 3 with a minus plus, and epsilon 3 epsilon 1 with a plus minus. Then we translate between vectors and spinors, as we have been taught to, and use momentum conservation to simplify the resulting ratios. So we already start to see that by dotting with P, we already get the 1, 2 angle bracket, right? So we get the 1, 2 here. The remainder is to account for these angle square ratios. And these, you use momentum conservation to simplify them. So what we then do is convert these ratios. So okay, you can go through these rules and you find that there's 3 sigma squared, 3 zeta squared divided by 1 zeta, 2 zeta, and then those with momentum conservation will give you the ratios that will complete this expression to look like this. So not this. And so we're cool. It's believable, but then of course, go on shell and it'll all go to 0 if you're in, like in regular Minkowski space, for the reason that we just described, that if you just don't entertain the complexification, this really will be 0. Okay, so finally we get to the first fancy acronym that I was ever exposed to during my time as a PhD student in the same institute as Freddie Cacciazzo and Matt von Hippel at the time when he was a postdoc at Perimeter, which was the BCFW recursion relations. And then there's many strings, like many acronyms in this field, which we can maybe go through further editions of this. But this is a good first one to start with. I mean, is there a simpler one than this? I wonder, Matt.
Uh, as an acronym or as an introduction to
No,
the field?
the latter. I don't mind how long the acronym is. It can be all the letters in the alphabet.
Yeah,
I care.
no, BCFW is probably a good introduction. There's a few kind of early developments. There are things that happened before BCFW, but it's maybe kind of the cleanest thing that you can show someone with just, the pieces walked through, show them why complexifying momenta is good, show them that you can build something purely on shell and that it works nicely.
Okay. So it's not a bad one to start with. So the review starts by expressing the conundrum with complexification that we touched upon earlier in this discussion, which is that, well, amplitudes, everybody believed they could be determined from their analytic properties. And so what people did in reference 40 in that set of notes was to complexify Mandelstam invariants and study amplitudes as functions of these. But they complexified too much. And, it's funny because even Weinberg talks about why he didn't get too deep into what was S-matrix bootstrap at the time because of the complexity of like multidimensional residue theorems and all these sorts of things, which he didn't sort of see how to cut through. He developed effective field theory instead, which I guess was pretty cool. But I guess the point was that this is not the Goldilocks zone for complexification. Whereas Richo Cacciazzo, Feng, and Witten figured out what was the Goldilocks zone, like sort of how much to complexify without having to wrestle too much with multidimensional residues and all these other things. So what they did was said, well, let's just look at how we can sort of map the singularities of tree-level amplitudes into poles of in terms of a single complex variable, so that even somebody who's just been introduced to basic complex analysis can appreciate what's going on and possibly tackle these. So they say consider a tree-level n-gluon amplitude and introduce the following deformation of the spinors of two adjacent particles 1 and n. This is sort of like the cyclicity of these particles that explains why adjacent is referred to. Why 1 and n are referred to as adjacent. So they say take lambda of 1 and lambda tilde of n, and then subtract and add minus z lambda n and plus z lambda tilde 1. Now, this is just some z, not to be confused with the generator of the helicity transformations that was shown before, where the lambdas were transformed by z and lambda tildes were transformed by 1 over z. Here, this is just a sort of additive transformation by some. This is a deformation. This is just you take some complex number, you subtract off lambda n times z from lambda 1, and then add lambda tilde 1 z to lambda tilde n. Cool. Now, what that means in terms of the momenta of P1 and sort of Pn is that instead of just having the simple product form of lambda tilde lambda, they're going to have the following shifted product form where it's lambda tilde lambda 1 minus z times lambda tilde 1 lambda n. And similarly for Pn, it's lambda tilde lambda n plus z times lambda tilde 1 lambda n. And the nice thing about this deformation is that momentum conservation and the on-shell conditions are preserved. So you can sort of have a family of momentum conservation conditions under this deformation by Z, and similarly like the on-shell conditions. Which means that as far as amplitudes being the things that look like on-shell amplitudes look, so if we were to take this kind of definition of what the amplitudes are, then this deformation just generates a one complex parameter family of amplitudes. And there's something to be gained by understanding the continuation of the original amplitude in the complex plane of Z. So now, what are the analytic properties of AN of Z? So tree-level amplitudes have simple poles in multi-particle channels. Well, I guess this goes back to what you were saying, that tree-level amplitudes are rational functions of the kinematic data. And just from knowing that tree-level amplitudes are vertices sewn together with propagators being inverse functions of momentum, well, really inverse functions of the sort of free particle Hamiltonian, we know that, well, we should expect that when the momentum goes on shell, the propagator is a 1/0 looking thing. And so that's a pole in the amplitude, which, no other integration has been performed, right? It's just sort of different vertices sewn together by these propagators, is sort of product of all these things. So you should just expect that, well, the residue is, or rather, the poles are just going to correspond to what happens when these momenta go on shell. And so the residues, well, they'll just be sub-amplitudes, right? They're just going to be like lower point amplitudes, which are all, again, on shell, because that's sort of what's going on there. So here, the multi-particle channels are really like exchange of like on-shell particles, right? So that's where you actually see the pole. So long as they're off-shell, we don't care. Cool. And so this is what they comment on. The Feynman diagrammatic expansions pick up all diagrams that have a propagator 1/p², where p is the sum of momenta. And as p goes on shell, the singular diagrams combine into a product of amplitudes on the left and one to the right of this propagator. So it's like in pictures, this is sort of what I described. So you have some set of vertices sewn together with propagators, and you have some external lines. That's the tree level amplitude. But now let's take one of the propagators to go on shell. Well, for our purposes, let's take the one which involves the sum over all the momenta to go on shell. Then what's going to happen is you're going to have two amplitudes, sub-amplitudes of lower point on either side, appearing as residues corresponding to this pole. And I mean, the easiest way to see this I found was to just like work it out for like some scalar field theory. It's a little bit more painful to do for gauge theory, but not too painful, provided you choose a nice gauge and everything. But anyway, here is what happens to AN sub Z. So AN sub Z has precisely n-3 simple poles in Z. So with big P sub I being the sum all the way up to I-1 of P sub J. So J starting from 1 to I-1 of P sub J. What we have is that the shifted, so now shifted in terms of this deformation by Z, P², so that's I over regular P² minus Z times PI, which is then, like we're using the 1 and n from the solutions to the Weil equation that we saw before. So there what we see is that there are, okay, so let's see why there's n-3. So this I haven't fully understood just yet. So could you walk me through this, Matt? So we've chosen...
Yeah, so... Sorry, go ahead.
I mean, is it because we've chosen sort of like 1, n, and I as sort of... yeah, well, I guess given that P separates these two sub-amplitudes, well, there's the one momentum, which is the sum of all of these, vector called I. Then there's the two neighboring in the sort of cyclic order momenta I, or sort of 1 and n. So those are like three that stand aside from the rest. So you're gonna have those three poles. You can sort of have any one of those three go to 0. And each of, or rather you have a sort of, each of them going to 0, giving you a pole. So that,
yeah, no, that's exactly the right way to think about it. That you fix things that you're shifting, so you can't mess with them. And due to the form of the shift, the particle adjacent to one of these things also can't be shifted because it's involved in the expression you've got for how the shift works. So everything else, though, is fair game.
I see. Good. So 1 got shifted, n got shifted. I is just stuck in the middle of so that's sort of what we're doing here. So cool. We have this resulting expression. So 1 over p squared. Z is 1 over p in this sandwich between 1 square and n angle with I over z minus z sub p I. And now the poles are at these three positions. Well, yeah, so this is sort of where I expect this denominator to vanish is when you have p over, well, yeah, basically when this thing vanishes, right? And that's just p squared I divided by this sandwich thing for all the i's that are not 1, 2, or n, or 1 I and n. It's just this funny convention. But
no, it's 1, 2, or sorry. I mean the I is the thing you're allowing to vary still.
Yeah, sorry.
The point is that 2, yeah. It's not that I is special. I mean, it's just never when you're looking at it. 2 is special.
2 is
because
special,
2
right.
is involved. Yeah, because 2 is involved in the shift that you're doing.
Oh, right. Well,
and we can kind of, maybe it's better to sort of scroll back to the definition of the shift just to show
but
this. Yeah,
the funny thing is really that they want 1 n. So sort of the shift is between 1 and n. And yeah, whatever. There's been a little bit of a change in labeling, it seems. So fine, okay. That's where we expect there to be these poles. And then we have A factorizing in the following fashion. So these two blobs are basically AL and AR, where now the shift is seen in 1 minus p to the power minus h, p to the power h, and n. So let's see. Why do we have these two objects appearing here as the arguments?
So these are the
So these I expect on account of, well, the shift that I originally started with, and then evaluating. Well, so I mean, if I were to think about this as the residue, and I go take Z to ZP, then yeah, I expect the shift to evaluate the argument on ZP. But where does this come from? It's still sort of confusing me.
Yeah, so these are the particles going across your across split, right? So the particles on either side of this factorization. And these are going to depend on the momenta, and thus they're going to depend on your shift, because one of the momenta flowing in is a shifted momentum in each case, either one on one side or n on the other.
I see.
Incidentally, I think I kind of described the role of 2 a little incorrectly before. A better way to think about it is that AL needs to be at least a 3-particle amplitude. If it's a 2-particle amplitude, it doesn't exist.
Right.
So you need at least something to stay on that side, and then I is on the other side.
Okay, cool. So that's I see. That's where this happens. Okay, yeah, okay, and then the sort of cyclic nature of this entire thing is preserved. Cool. But I guess so the takeaway is still that these are lower point amplitudes than this, and that in principle, knowing the smallest object here, as you mentioned, being the 3-point amplitude, right, which is what we had up here, well, here or here, we could in principle get to some higher order ends over here. Very cool. So yeah, that's precisely the point they make. They say we only really care about an at z equals 0, and one way of setting z to 0 is to just look at the contour integral around the origin of this object. And this is just, well, when you're doing complex analysis, this formula is almost as good as integrating against a delta function. I mean, they're sort of subtly related. Um, and well, I mean, in some very precise sense, they're related. And what we will find is that the residues of this object allow us to construct it completely, and we know what the residues are. They're given in terms of these AL and AR objects, plus a residue at z equals infinity, which I suspect we're allowed to ignore, as we tend to.
Well, yeah, or
In
at
most
least if you can't, it doesn't work, is maybe the statement.
okay, great,
And
yeah.
so, I mean, we have a term. Some theories are BCFW constructible, and some are not.
Mm-hmm.
And the
I
theories
see.
that are BCFW constructible are ones where you have some argument that this vanishes.
Cool. Okay, that's cool. So and that basically requires that a n of z goes to 0 as z goes to infinity, um, which is when you can basically drop that. But is there a case where this is calculable? I'm just curious.
Yeah, you mean calculable and non-zero?
Yes,
Um,
calculable and non-zero.
Yeah, so I'm having trouble thinking of it off the top of my head, but I mean there have been sort of a few cases where people have tried to extend this formalism to cases where there's some kind of known thing there that just doesn't happen to be zero. Again, it's much trickier to extend it that way because you need it in the context where for some reason you can calculate that. So particular, just you kind of have to assume something else about the amplitudes typically. You kind of can't build it in as a minimal set of sums. But
Interesting. I
yeah.
see.
But I mean, luckily, sort of all the cases that we like either kind of have this property, or I think I don't know if they discuss the situation with gravity here. With gravity, it doesn't quite have this property, but it has enough of it that you can still do BCA.
Very cool. Yeah, I mean, I well, haven't gotten as far as gravity just yet. But yes, they do talk a little bit about the vanishing of the boundary term, and that's equivalent to just having the contour and circle infinity rather than the origin, and that sets some fall off for what a n of z should be, and yeah, I guess that just goes to a criterion that the amplitude must satisfy that needs to somehow be checked. So well, that's yeah, no, that's very cool. So basically what they're exploiting here is the ability to sort of complexify just enough, which is sort of two spinors. It's really one momentum's worth of degree of freedom, but it's split between two spinors, which I guess is a very clever thing to do. And then there's this very cool way of exploiting this otherwise nice and sort of cartoonish fact that like tree level amplitudes have their rational functions with residues or with poles appearing when there's an exchange of a non-virtual quantum, like a real quantum, and that the residues are products of lower point amplitudes. And of course, the starting point for this, you need some minimal a, and then that, knowing the 3-point function or the 3-point amplitude is a great uh, is of great help here, because you can sort of like presumably kick this off starting from there. Nice, I see. So this is as much as I had prepared beforehand, but I guess, I mean, one can go back and read more of the review here to sort of see how this applies to gravity and beyond. And just to give a sort of teaser of that, you say that there is a BCFW recursion relation that you can apply to gravity as well, or it's sort of the same thing. Very cool. That's very cool.
Exactly.
And then there's also stuff that we've sort of jumped over, which is sort of color dependence, and there's a lot of games to play where there's the taking into account of color kinematics, and then swapping these things out. So I guess one thing that we haven't really touched upon at all is all these sort of copy relations, double copy, and so forth, sort of all string inspired. But yeah, I mean, this is a really cool field. What sort of excites you? So sort of switch gears into talking about like the frontier. So you get to the end of the alphabet. So what sort of excites you about the most recent developments in this field? So like maybe from the past 5 years, which we'll say is sort of recent enough.
Sure. So, I mean, one thing that's been kind of impressive, though, there's the conceptual bits, but it's also kind of practically impressive, is just how fast Amplitudes people have begun to kind of tackle rotation amplitude much more directly useful context with LIGO and Virgo with the gravitational wave telescopes. The idea there is that a lot of these same techniques, you can use them in some effective field theory context to actually talk about classical dynamics of, say, colliding holes.
Mm-hmm.
And so there's been an enormous kind of revolution in amplitudes methods developed with this. And on a conceptual level, one of the kind of coolest aspects of it is this sort of dictionary between things that we're used to talking about in a very quantum context, scattering amplitudes, and nice classical observables. There's formalism, which is another one of these 4-letter acronyms, in this case, KMOC.
Mm-hmm.
That have to do with kind of taking things like, say, the impulse, something that's a perfectly reasonable classical thing, and talking about it from some sort of quantum derivation.
Interesting.
Yeah. In terms of kind of where I'm seeing things going, I mean, one I'm very concerned about is the sort of spaces of functions that show up at loop level, because
Mm-hmm.
okay, trees, they're all rational, that's fine. One loop, the polylogarithms, which again we haven't talked about in this edition of the podcast, but they're a nice, well-behaved space of functions we all know how to deal with now. But gradually you start getting stranger and stranger functions, and you can think of these things usually as iterated integrals involving various kinds of algebraic varieties.
Okay.
And kind of the first few are things that you can think of just on the integrals on a Riemann sphere, integrals on a torus. But then you have things that are involve higher dimensional varieties. And in particular, for some bizarre reason, and this may just be a spotlight, not spotlight effect, effect, the ones people have looked at have been connected to Calabi-Yau manifolds, which
Interesting.
has been a very out of left field development. And the thing
Okay.
about these things is that, despite them having these sort of weird algebraic geometry sitting inside them, they also are going to show up in these practical calculations. So right now, if you talk to the amplitudes people whose main focus is on calculating the LSE, what they're doing right now is they're doing 2-loop amplitudes, and they're trying to do it with 5 particles, and they're trying to gradually make more and more of those. And they've gotten to the point where they can add a mass, they can add two masses, things are kind of working. But once you get to adding three masses to this, then one of the diagrams you might have to consider involves a K3 manifold. So within, a decade or so, there will be enough data that people are going to want to calculate these kinds of things. And I think it's a very big question, kind of how we think about these sort of stranger function spaces.
Cool. So just to get some context, so it makes sense that like loop amplitudes will involve iterated integrals just because you have loops, and you're gonna have like whatever Schwinger parameters running between a few things. Is it just that these varieties you're talking about arise from like some enlightened way to look at whatever jumble of integrals over like the Schwinger parameters that you would normally get by applying the sort of Feynman rules and proceeding, or is there some additional magic to this story?
No, I mean, I think that's a good way to think about it. It's not. Sometimes you have to do very strange things to the Schwinger parameters to get these things to manifest, but sometimes it just stares you in the face.
Okay.
The first diagram of this form that people were dealing with, you write down the Schwinger parameterization, you do one integration, and there is, a very recognizable form for a Calabi-Yau manifold that you can even, dial up the dimension with the loop order in a very nice organized way.
Nice.
So there's examples that are just totally crisp like that. There's also examples that are weirder, that I've explored several where you can kind of uncover these things if you use sort of an unconventional variant of the Schwinger representation and you do some particular path of integration, and then you get something showing up that's weird.
I see.
I don't think there's no general theory.
I see. I mean, the reason I ask is because there is, at least with the whole copy story, there's this intuition that, like all these massless particle amplitudes, despite the fact that there's some massive sort of double copy relations people talk about, but setting those aside, if you just looked at these massless particles, then, well, shouldn't all their amplitudes just come from like, some limit of string amplitudes, and you have this relation that started in string theory, and okay, you can kind of see a shadow of it appearing in field theory, which kind of points, and there are ways to make this, at least from what I have gathered by going to talks, there's ways to make this kind of intuition semi-precise, and in much the same way as whatever's going on there. Here, when you talk about Schwinger parameters and everything else, I mean, these are, they're really like some boundary manifestations of what would otherwise be like string moduli, right? They're sort of like some sort of thinned out version, whatever's going on there. And of course, like K3 surfaces, Calabi-Yau manifolds are sort of like some very favorite backgrounds for.
Sure, but backgrounds, not objects
Indeed.
that show up in perturbative string theory calculation.
Indeed,
so
indeed.
It's coming at it from a very different direction, and I mean, people like them as backgrounds for very distinct reasons because they preserve supersymmetry, for example.
Right, yeah.
Yeah, and these examples, some of them are in supersymmetric theories, most of them are not. Most of them have kind of nothing to do with that sort of context.
Great.
So it's really manifesting in a way that string theory doesn't kind of provide a clear suggestion for. I will say that for double copy, it also feels like it's general than what it could come out of string theory. I mean, even setting aside the massive cases, the impression I get is that there are examples of theories that seem to be together by these double copies that do not seem like they should be representable in string theory.
Interesting.
The one example that's coming to mind, I'm not actually sure whether it has masses or not. These kind of so-called magical supergravities.
Okay.
Yeah, there's if we had another one of these conversations on double copy, or if you brought in someone else who was more double copy focused to do it, They have these giant tables of, all the different things double copied together into different things. Sort of the standard meme of the guy with the
Uh-huh.
board, sticking all the threads together, right? And many of these things are very strange things.
Okay, well, I'll bring a board for that one. Whether you volunteer to do it or anybody else. I mean, of course, it would be great to have a follow-up discussion on just these function spaces and sort of getting a feel for how it is one discovers K3 surface without necessarily intending to, in contrast with what goes on in the business of finding nice string backgrounds where you just say, well, I just want so many killing spinners to appear. And well, it seems that the only way for that to happen is that the space looks like this. So I mean, like it would be very cool to talk about that too. But when it comes to the sort of broader sort of thematic motivation of getting to the identity of the fields themselves, there's a sort of line you hear from various people, the Amplitudes community, where they're fairly confident that we don't have a clear enough picture of what fields themselves are, and that's manifest by the fact that there are these simple relations we discover by going on shell, complexifying this or that, being very clever, that we just don't see starting with the Lagrangian. And it's ironic because, as we discussed, some of these things came out of computing string amplitudes, where in many ways string perturbation theory is limited by the fact that you don't have the analog of a Lagrangian from which you could derive all of those vertices and rules. And this seems to be a way of sort of spinning the defeat into a sort of victory and just setting aside the fact that whatever, string field theory is hard. But anyway, sort of setting aside all of that, where do you think the frontier lies in that direction, the direction of that question of knowing the identity of a field or fields in general?
Sure. I mean, one thing that's recently become quite prominent in the field and that's kind of impressed me about how much one can do with it and how far it might go, shall we say, um, is this set of kind of questions about if you just try to impose some sort of general condition on scattering amplitudes, how much can you learn from that?
Mm-hmm.
So, in particular, in the context of kind of effective field theories, where you've got
Mm-hmm.
room for various coefficients, and then the question is, okay, what's actually allowed? So this is, there's very similar methods to the conformal bootstrap, where instead people are imposing positivity constraints, people are imposing causality on, say, gravitational amplitudes. And when you do this, you start kind of carving out a space of effective field theories that are permissible and that they just lead to causal evolution, in much sort of stricter constraints, or I should say, much sort of more grounded constraints than, say, the swampland program, just kind of saying, okay, we need something that makes sense.
Mm-hmm. Mm-hmm.
And actually getting kind of meaningful limits on what's allowed and saying, okay, well, it looks like for gravity, you actually get something like the sort of dimensional analysis naturalness lore that everything needs to have certain scaling in terms of the cutoff scale. Like this is
Mm-hmm.
actually something that is a rigorous bound in the case of gravity. And in the case of some of these kind of scalar theories that are derivatively coupled as well. And I think that kind of thing has a lot of potential, both in this kind of context of this sort of, deeper goal that everybody has of, can we talk about the world purely through these observables? Can we say, okay, here's, observable bad consequences. Can we use this to constrain all of our speculations? But it also kind of feels like the right approach for physics going forward, in a sense.
Mm-hmm.
That if you kind of think about the Large Hadron Collider, one thing that people could be doing there is looking for particular things. But as the Large Hadron Collider continues to run, nobody is seeing any of the particular things they're looking for.
Indeed.
Really, what I think is productive is to think about this in terms of a set of constraints, to say, look, let's just in full generality describe our ignorance and say how much we actually learn. We have this device, it's giving us all this data. What's the maximum amount of information we can wring from it? So these sort of standard model effective field theories that kind of try to say, okay, what's the next few corrections, assuming some basic things that we're usually happy to assume. And if you want to work with these kind of things, you need to make sure that what you're working with is actually a space that makes sense. And so these kind of positivity causality constraints are an important addition to it. They mean that you're not sort of exploring just arbitrary parameters. There's some story which things make sense and are really the open questions as opposed to merely kind of artificial open questions.
Indeed. No, that I think is very cool. Yeah, so I mean, I suppose, one thing that we haven't come full circle to is, at least in theoretical physics, is a lot of talk about how most fundamental theory now is not guided by any data because, well, you just can't build a large enough detector. But what you're saying is that's not actually true. If you're paying any attention, you realize that the kind of theory that does respond to the kind of data we're getting is the theory of this kind where you constrain parameter spaces to then fit the kinds of data you're getting, right? So if your prior is to say we want spontaneous supersymmetry breaking near sort of the scale of where you expect to have ultra-weak symmetry breaking so as to have all of the cool things with the unification and whatnot, then it makes a lot of sense to just hold your breath and wait to see whatever it is we expected to see back in the day. Once you don't see it, then we're left with making sense of a world where there's, you have a standard model Higgs, seemingly large hierarchy of scales, and well, what do you do in that setting? So you had just that and nothing more. Then where do you expect? I mean, even to just sort of situate where rest shall show up, where the rest shall show up, you need to sort of have a nice framework for it. And yeah, that I'm very sympathetic to. And it is cool to hear that, these sort of positivity constraints, in some sense, make sense of that, sort of like what you said about having these sort of hierarchy expectations reflected in properties of these amplitudes for them to sort of be consistent is cool because it just tells you that, well, were it not the case, we would be living in a stranger world. And that I think is nice. And I do feel like, I mean, do you agree with the sense that the kind of data that we now have access to, which is either seemingly exciting stuff on the high energy front and very detailed stuff on the relatively low energy front in the context of, say, quantum matter or whatever, it leads to the development of theoretical tools that maybe broadly fall under, say, bootstrap or generalized bootstrap type ideas. I mean, is this sort of just a correlation in your view, or is this like a sort of one motivates the other?
I mean, I don't know too much about the history of it, right? I would assume that, of course, a lot of his bootstrap research is kind of interfacing with, the concepts in which informal theories show up in statistical physics. So, but I don't know enough of the history to kind of see how that story developed. I would certainly think that it had an important role, but of course, so did kind of early investigations of string theory and things like that. Yeah, I mean, I also don't know how directly tied in they are with the kind of experiments people are doing, whether there's this kind of back and forth. I know in some corners of that field there are.
Sure. Yeah, I mean, I was just saying that this is maybe a little bit more thematic because it sort of moves away from what people were doing before, which was to sort of try and identify some players in the game of high energy physics or in whatever. There was a time where they were like, well, it's probably these relativistic little extended rod objects that sort of spin really fast. And then they're like, no, it's these other things called the quarks and the whatever. And then they were like, yeah, then there are these super partners for all those other things, and that's what we expect to see. And now we're not saying any of that. We're saying, well, here's a function space, and here's a bound on what kind of parameters you can have. So yeah. So is there an effort you can identify to then do the old-fashioned thing? So what's the fast, spinny, relativistic thing object of our
Okay,
our era?
sure. I mean, there actually no. I mean, there actually is a direct analogy with this, and in fact, it's all appropriate because the main proponent of this um, direction is also the person who's most famous for saying the universe is not a metal.
Mm-hmm.
Right, and so this is the sort of, you might say, the amplitudehedron perspective. There's kind of other lines of research along those lines too, but this is kind of this idea that, okay, what you need to do is you need to take our expertise in expressing amplitudes in various sort of weird ways, um, and find representations that make different kinds of properties manifest. Find representations that are at their heart not these kind of stories of particles in space-time, but that are instead combinatoric geometric kind of objects.
Mm-hmm.
And I think that's in some ways kind of the heart of what specifically Nima Arkani Hamed, but more generally, a lot of people who have either bought into this particular direction or have kind of developed things similar to it that go in sort of different ways. What the kind of aspiration there is. It's saying, okay, look, well, if you want fundamental, if you want one principle to rule them all, it's going to sort of be some deeper mathematical notion. It's not going to be these kind of nice story like to tell about fields. It's not even going to be these nice stories we like to tell about particles necessarily. It's going to be some sort of geometrical question that has some kind of geometrical answer, or some combinatorial question that has some combinatorial answer. Yeah. Things that have a sort of purity to them. And so what you do
Right.
is you kind of find, for different theories and different contexts, examples where instead of asking a question that, like, okay, perturb this Lagrangian, what you get, you find that the amplitudes are the answer to some geometrical or combinatorial question. I think the hope there, and nobody's really taken this next step because I think people are still very baffled as to what it would be, is that there's other such questions that give things that are kind of like amplitudes, but not quite,
Mm-hmm.
and not
Mm-hmm.
quite in a useful way, not quite in a way that might solve some deep problem.
I see. Very interesting. So did you hear that, Nima? This is an invitation for you to join this podcast. Um, email can be found in the description below. Uh, yeah. Such aspirations
I mean, you
aside.
should try. I mean, yeah, I mean, well, you should try, and if not, talk to one student
Yeah, yeah. Happy to talk to
who are
anybody.
probably, or at least probably more reliably skilled.
Yeah, yeah. No, but this was fun. And indeed, I was hoping for you to talk a little bit about the various hedra, and where you see that effort going. But for better or worse, this is the physics of our century, at least in its novelty compared to everything that came before. And I do hope to one day come to appreciate what the point of it all really was, as I hope everybody does, in a generalized sense. So
Mm-hmm.
thank you for helping me lay out the first steps in that direction, Matt. I do appreciate you taking your time. And for those who don't know, Matt is a blogger and has been for many years. I'll leave a link to his blog for gravitons in the in the description. Is it still called that? Just to
It is
check.
still called that, yes.
Very cool. And yeah, I mean, you blog about various things, a lot of it having to do with amplitudes, but not just. So yeah, no, it's a fun read. I recommend people check it out. So yeah, thank you, Matt.
Well, thanks so much for inviting me. It was a lot of fun.
Cool. And thank you all for watching. If you've gotten this far, please leave a like, subscribe, comment, share, and I will catch you next week for another edition of Theoretically Podcasting. See you.